we will have the very last lecture in chapter 10 of our textbook. So we'll be officially done with the lectures in an introduction to statistical learning with applications in R. The last topic we have is about clustering. That's another tool we have for unsupervised learning. And in clustering, we want to show that how to classify or group some data into subgroups, or in other words, how to partition our data into distinct groups in terms of the similarities they have in our feature space. So one thing I have to emphasize is that since we are dealing with unsupervised learning, we do not have any idea what the labels of these groups are. We do not know these groups a priori. So let's look at the distinction of clustering and principal component analysis. In principal component analysis, we look at low-dimensional representation of the data, which represent most of our variation of the data. However, in clustering, we look for homogeneous subgroups among the observations. So let's say we have a large number of measurements. For example, median price of homes, occupation, distance, whether you're the nearest urban area from this distance, and so on and so forth. And let's say we have these observations for different people, and we want to segment them together. We want to cluster them together so that we are able to send them particular type of advertising or particular form of advertising to target them individually. So we want to find the similarities and then send most effective means of advertisement to them to target them. So in order to find these market segments, we have to use clustering techniques. We have two clustering methods that we're going to explain. The first one is called k-means clustering. It assumes that we already have k number of clusters. So this is given. The second one is called hierarchical clustering. Here, we do not know in advance how many classes we have, and then in fact we end up with three like visual representation, which are called dendrograms, and then it allows us to choose any level of number of clusters that we want from them. So let's just start from k-means clustering. As I said, k should be fixed. So here we have same type of data set, but we have fixed number of clusters we have to 2. This is the first class we find here. This is the second class. If we fix classes to 3, these are the 3 classes we find based on the k-means algorithm. And 4 classes this one, okay? So in k-means algorithm, what is important to remember is k should be fixed. And how do we fix k? What is the best number of k's we can use is still debatable in literature. That's a part that is still researchable. There is no consensus over it. So in k-means clustering, we assume we have ck categories, ck clusters, and they're collectively exhaustive. That means the union of these clusters entails all of our data points. So there is no point in our data set that doesn't belong to any of these clusters. The second one is for 2 distinctive classes, they do not have anything in common. So that means any point belongs only to one of the classes, not 2. So in general, we want to minimize the within sector variation. This is within sector variation. Okay, so we want to minimize the within sector variation, within segment variation, within cluster variation of these values. So that's what we want to do. So we want to cluster them such that the within cluster variation is minimized. So that means for all classes, if we have k classes, these variations among my observation in each class summed up is minimized. So let's see how we can do that. Officially, we can just show that the within cluster variation is the differences of 2 points in each cluster squared summed up for all classes. So let's say these 4 points are in one cluster. So this is one distance squared, this is one distance squared, this is another distance squared, and so on and so forth. So summation of all these distance differences for one group divided by total number of observations in each group summed up over all groups. We would like to minimize this amount by picking correct clusters. And we can show that the correct CK is that broken in the feature space of M is giving us the best model. It's relatively easy to use. There is a very efficient algorithm that gives you always local minimum for this function, and that is based on the following algorithm. So I think it would be easier for me to explain it on a figure of it. So let's first look at it clearly, and then I say what it is. Suppose you have 3 clusters. So my assumption here is we have 3 clusters. So in first step, we randomly assign these points to each of these clusters. So we assign 1/3 of our observation to one cluster, 1/3 to another, 1/3 to the last one. So we randomly pick greens, pinks, and yellows. Or you can, that's one way to do it. So you randomly pick that, and then you take the average of all green points. So the average of all green points is this green dot. And you take the average of all red, golden points, that will be this point. Then you take average of all pink points, and that will be this one. So in step 3, you color these observations based on this, the closeness to each of these points. For example, this point is closest to gold, so we assign gold category to it. This point is also closest to gold, but this point is closest to pink. This point is closest to green. So we just assign the colors based on the closeness to this centroid point. So we get step 3. So here again, we take the average of all green categories, pink categories, and gold categories. Okay, so that will be our new averages. And again, we repeat whatever we did. So we color all the closest points we have to this point based on the colors they have. So some of these observations may change. For example, look at this value. This is so this point was closest to this. That's why it was painted as gold. But now, when we changed our mean based on the mean of all observations, we get this. And for green, what happened was that this point turns out to be closer to our new mean. So you repeat it over and over again until your centroid is fixed. So in 2 iterations, nothing will change, and the assignments are fixed. And that's a local minimum you have. Officially, what it means is that what you need to do is, in step 1, you randomly assign it to clusters. One other thing you can do is just randomly pick 3 centroids. So let's say that is another way to do that. So just randomly pick 3 centroids and assign closest ones to each one, closest observation, and repeat the same algorithm to get here. That's another way to do that, but in your textbook, that's the way it's been done. So you randomly assign the clusters, then take the average of those clusters with the centroids, then assign observations based on the closest of those centroids, take an average of those centroids, assign observation based on the closest of the centroid, and repeat it over and over and over again until the time after 2 iterations, nothing would change. So one thing I want to emphasize is that this algorithm gives you a local minimum. A local minimum means, for example, in this function, my global optimum point is here. My local is here. The local minimum is somewhere that has first order derivative equal to 0, so partial derivative equal to 0 in all directions. So this algorithm always guarantees that you will end up with the local minimum. It may converge to global optima. So here we have 6 different observations, 6 different algorithms with 6 different initial points and initial random assignments. As you can see, the error we get from this assignment is 320.9. This assignment 310.9. These 4 assignments is the minimum you can get, which are identical. Forget about the colors; they're just representation. For example, here is gold. Here, the gold here is just pink. Okay, so they're the same categorization. So these 4 cases ended up with 235.8. So this is my global optimal, these 4. These 2 were just our local optimal. So one of my suggestions for you to use k-means clustering is that to do that, just use different random assignments and choose the minimum you can get. So repeat this algorithm over and over again, and each time when you converge to a new point, just choose the one that has the lowest amount of error. So that is basically what I explained earlier. So k-means clustering requires pre-specified k. That is somehow disadvantage of this algorithm. We're not going to discuss how to choose k. It's beyond the scope of our lecture. But what I want to make sure is that Dr. Tibshirani and Hastie have another book which was prequel of this textbook of Introduction to Statistical Learning. There you can find good information on how to choose k for those who have better understanding of math. I suggest you work on that. But let's work on another algorithm and see how does this one working. This is called hierarchical clustering method. There are a lot of ways to do hierarchical clustering method. One is bottom up, and that is the most famous one. So let's focus on that one. One of the great things about hierarchical clustering algorithm is that you end up with clusters, and you can use the number of clusters that you want based on the tree-shaped clusters that you get. That's so awesome. And whenever you use this algorithm, you end up with dendrograms. This is a type of tree-shaped plots. And based on that, you can cut it from anywhere you want. And based on where you cut it, you get different categories. So let me show you what is the bottom-up algorithm look like. The bottom-up algorithm first finds the closest observations you have. So in first step, you find the closest observation. This is my closest observation. So it clustered them together. Then it looks at the second closest observation you have and considers this cluster as one big observation. Okay, so my second cluster might be B assigned to A and C or D and E. So I think D and E are closer than B to A and C. So in second step, D and E was chosen. In third step, it chooses what this observation, where this observation is closest to, and here it seems like A and C is the answer. So that is my third clustering, and at last it clustered everything that is remain. So if you want to show it in dendrograms, it shows that the At first step, the closest observation was D and were actually A and C. In second step, D and E were clustered. In third step, B was clustered to A and C. And at last, they were all clustered together. They become a single cluster. So now, if you want to decide how many clusters you want to have, you can pick how much error you want to tolerate, so how much differentiation you want to tolerate. So if we cut it from here, we will have two clusters, BAC and DNE. If we just cut it from here, we will have three clusters, AC, B, and DNE. If we just cut it from here, we will have four clusters, AC, B, E, and D. So here we have 45 observations generated in two-dimensional cases. This is a simulated data, so we actually know the labels, but we don't want to use the labels in our training algorithm because that's unsupervised learning. So we basically had four clusters. So let's see how our algorithm is doing. It is shown that the algorithm clusters these points this way. So depending on where we cut our dendrogram, we get the cluster one. So if we cut it correctly, we get exactly three clusters corresponding to the three clusters we want. If we cut it here, we just get two clusters. So basically, you will cluster these two together. Okay, so you can have any number of clusters you want based on where to choose dendrogram. Okay, and here is another example. It starts from clustering 7 and 5. The way we find is that gives you the minimum error. So 5 and 7 were clustered first. They became one cluster. Then 1 and 6 were clustered together. After that, 8 was clustered to 5 and 6, so they became one cluster. After that, 4 was clustered to 1 and 6. After that, 2 was clustered to these 4. After that, 3 was clustered to these 3. Later on, 9 was clustered to these clusters. And lastly, they were all clustered. Oh, it looked like two eyes with... Let me put a smiley face here and the nose. Okay. It looks interesting. Okay. So that's how clustering part worked on. And so one thing that you might have already asked yourself is that how do we, if we cluster two values, how do we decide what is the closeness of these clustered values to another value or another cluster? For example, what is the distance of this cluster and this cluster? In order to decide which value to cluster with, which clusters or which observations, we have to have a notion of how close we are to different clusters and different observations. But how do we measure that closeness? The answer is there are 4 ways to do that. Complete, single, average, and centroid. So let me explain each one. So let's work on complete. In complete, case, so let's say we have 3 observations here and 3 observations here. You find the distance of each observation with each observation of each cluster to each observation of another cluster. So we have 3 here, 3 here. So we have 9 observations here. So 9 2 by 2 comparison, and we just and between these observations, what we are going to do, we record the largest of these dissimilarities. So I think for complete, we will choose the distance of this guy and this guy. These have the largest dissimilarity. So that will be the linkage distance of these two. In single, we find a minimal intercluster dissimilarity. So we compute all pairwise similarities between the observation cluster A and B and record the smallest of these dissimilarities. For example, in single case, in single case, this distance will be chosen because these are the closest observations. In average case, we take the mean intercluster dissimilarity. That means we compute all pairwise distances, all 9 of them, and compute the average of them. This is actually a very common practice. If you complete an average, or so these two, so among these four, complete and average are the most common version. So here you average over all these similarities. So you compute what is the distance of this point and these three, this point and these three, and this point and these three, and average over all. That will be the similarity between these two clusters. And in centroid, you take the average of these observations, so this would be this point, and you take an average of this observation, that would be this point, and you take the distances of these center points. It's not undesirable at all. It's not desirable that much. Okay. Also, you may have a question how we define distance. Distance can be Euclidean distance. In some cases, it can be some other measures. For example, it can be correlation. It depends on the application. So here we have, in this part, we have observation 1, 2, and 3. So if you look at the similarities from Euclidean distance, you may conclude that observation 1, which is the gold one, and observation 3, which is the pink one, are the closest. However, let's say what you want to see is similarities between two objects. And here, if you look at the correlation, you will see 1 and 3 are so close. 1 and 3 go almost the same way up and almost the same way down. Almost the same way up and almost the same way up. So from the correlation point of view, 2 and 1 are closest. So it depends how you want to define your similarity. The two most famous versions of finding similarity is correlation-based similarity, and also Euclidean distance similarity. So Euclidean distance was being used earlier, and correlation is here. So usually in time series analysis, you're interested in correlation-based similarities more than the other one, versus usually in cross-sectional analysis, you may be interested in just the Euclidean distances that we have. Okay, so here we just conclude our course. Thank you very much for being such great students. I enjoyed teaching the course to you, and I hope you enjoy it as much. Feel free to contact me whenever you have any question. Thank you, and bye.